Welcome back to complex integration. So in the last video, we talked about the foundations of real integrals, and we realized that the real integral can be defined as a Riemann sum, where the partition norm goes to 0. We made this a function of the partition, and then we took a limit where the partition norm goes to 0, and we specified what that means. Now, I want to remind you that the data of the partition is the data of the ti's and the tau i's. I've drawn the ti's into this picture, but I didn't want to clutter it with the tau i's. The tau i's are the sample points in between the ti's where the function is actually evaluated. And then we calculate, these are the heights of the rectangles, these are the widths. The partition is defined by all of this information with the ti's and the tau i's. And in order to have a partition that works, in order to have a good partition, you have to have sensible ti's and tau i's. That means that t0 has to be a, right? If you don't start at a, then you're not estimating the integral from a to b. You must be definitely estimating some other integral. If it has to end with b, so that means that the last of these ti's, tm, must be equal to b. And furthermore, they have to proceed in an orderly fashion from a to b. That is, the ti's have to obey these inequalities, right? The fine print here is that t0 has to be less than t1, less than t2. They don't have to be equally spaced, and in this diagram, they're unequally spaced, but they do have to be spaced out between a and b, and they have to obey these inequalities. The sample points tau I have to be chosen nearby, right? If we always sample here, if this is tau 1, that's tau 1 over here, and it's also tau 2, and it's also tau 3, and it's also tau 4, then every time we sample a function, we're sampling it here, we're not going to create an estimate for this integral, so that won't work. The tau i's have to be chosen sensibly, and sensibly means each one has to be chosen to be within the range created by the corresponding rectangle, so that means that it has to be between ti minus 1 and ti. So these are some sanity conditions on the choice of the partition, which affects the whole Riemann sum limit definition of the integral in the real case. Now let's move on to the complex case. So here I want to imagine that we have some function, and let's just say for definiteness f of z, well, I should say f of z at this point. So usually the complex variable is called z. F of z equals, let's say 1 over z. Nice, simple, innocent-looking function that we can integrate. In fact, we know that the derivative of log z is 1 over z most of the time, but not all the time, so that's a little bit of a concern. And now I have an a and a b here. Now I want to caution you, often when we deal with little a and little b in the context of the complex numbers, it's because we have a single complex number, and that number is a plus bi. That's not what I mean here. I mean that a itself is a complex number with a real and imaginary part, and b itself is a complex number with its own real and imaginary part. And I mean to choose a and b, analogous here, to be the beginning point and the ending point of the integral. So let's imagine that we want to calculate the integral of f of z dz, whatever that means, and we want to give a definition of what that means from a to b. So now it's a lot less clear what to do. So we can be inspired by this case, by this example, and we can say, oh, we need a bunch of ti's, and we need them to proceed in an orderly fashion from a to b. And so we can draw a straight line here from one point to the other. We need them to obey certain conditions, like t1 less than t2 less than t3, like this. But those conditions don't make any sense anymore, because now there are inequalities among complex numbers, and the complex numbers are not even an ordered field, so those inequalities won't work. We also need sample points, tau I, which I suppose I can plot in green here. I didn't plot them here. Like, imagine the tau i's are plotted here. So we also need tau i's, and the tau i's have to be within certain regions, right? Tau I should be between ti and ti minus 1, right? But that condition doesn't actually make any sense. For exactly the same reason, the complex numbers are not an ordered field. And so that's a big problem. We have other problems here, and that would be that, like, what if b moves over just a little bit, right? So if b moves over to here, then the straight line connecting a to b would include 0. And then we might have trouble sampling there. We also have other issues to consider. in the real line, there is only one way, more or less, to get from A to B. You go upwards from A until you reach B, right? In the complex plane, there are many ways to get from A to B. We could go on a straight line. We could go sort of a roundabout here. And so there are actually many, many paths from A to B. And it's not obvious whether we should prefer one of them. If the straight line path is there, there's no obvious reason why that should be the one path that we should use, the straight line path from A to B. And in certain circumstances, the straight line path is unavailable. Like in this case, if the straight line path proceeded through the origin, then we couldn't use it. But we could use any of these other paths that I've sketched. So there are a lot of problems with just naively generalizing this definition to this definition. Now, we could still almost solve all of these problems. So let me suggest how we might try to solve all of these problems. We might say, look, it doesn't matter. Pick any path. Pick a path from A to B. Any path at all, okay? Let's call this gamma. It'll go from 0, 1 to the complex numbers, and gamma of 0 will be A, and gamma of 1 will be B. Okay, let's pick a path from A to B. And then what we'll do is, along that path, we'll put in waypoints. T1, T2, T3. We'll put waypoints. And also along that path, we'll put sample points somewhere along the path. Tau 1, Tau 2, Tau 3. Notice Tau 3 is now in this picture not on the straight line segment between T1 and T3. So that's Tau 3, and then etc. And then on the basis of this information, we could produce a Riemann sum estimate. Now, what does it mean as the partition norm goes to 0? Well, as the partition norm goes to 0, it must mean that these TIs get closer and closer and closer to each other. Now, this is an option for defining complex integrals, and it's not like what you'll find in most textbooks, and there's a reason. It doesn't work. It's the most obvious generalization of the integral from A to B in the complex plane. The problem is, you do actually get a satisfying definition of a limit here, but so let me say for this particular example, supposing you have an A here and a B here, and you introduce this path gamma, and you get this value here. Nice things happen. When you take the right analog of this partition norm going to 0, this thing actually does produce a limit, and it does have some value. The problem is what limit you get ends up depending on gamma. It doesn't seem to depend very sensitively on gamma. If you pick another gamma nearby, like this one, gamma 2, you'll actually end up getting the same limit. And if you pick a similar gamma, like this one, gamma 3, then you'll end up getting the same limit. And if you pick this one, you're getting the idea, gamma 4, you'll get the very same limit. So there does seem to be some evidence here that this definition would work. But then you go and you define a new gamma, like this, gamma 5. The same definition works. The partitions get finer and finer and finer. You do get a limit, but it's a different limit. It's off by 2 pi now. And then you check your work and you realize, oh, well, that really is the limit of that thing. So you take it, and the real explanation here is you went the wrong way or a different way around the origin. And the origin has some exciting behavior for this function, and so it causes things to go a little bit haywire. And so this is a problem that ultimately we cannot just ignore. We need to account for the possibility that different paths will have potentially different limits. And that means that we should not even be trying to define, what we're trying to define here is the integral from A to B of f of z dz. We should not even be trying to define that. That is not the right thing for us to define in the complex case. Because one way of getting from A to B will end up having an integral, having a limit, but another way will end up having a different integral, a different limit. And so we cannot even really hope to define the integral from A to B of f of z dz. What we can do is we can define the integral from A to B along a particular fixed path. And so that's going to be the path integral. We can define, well, that's going to lead us to the path integral there. So basically what's going on here is, in the real case, how you proceed from A to B is obvious, right? You go along the real interval that connects A to B, and there's only one of them. In the complex case, how you proceed from A to B is not obvious, and it needs to be incorporated as part of the definition, part of the notation, part of the definition, and part of, what we recognize that the integral potentially can depend upon. And so we introduce not a definition of the integral from A to B, but the integral effectively of from A to B along gamma. And let me show you how we represent that. So our second sort of preliminary effort here is, preliminary definition. We might take the integral from A to B, the integral along gamma of f of z dz to B, and now what I'm going to do is I'm going to basically use gamma to determine all of the waypoints. So here's A, and here's B. Gamma goes from 0, 1 to the complex plane. Gamma of 0 is A, and gamma of 1 is B. So A and B are now missing from my notation, but they're still there because they're the endpoints of gamma. They're the gamma of 0 and gamma of 1 in that notation. I'm going to define the integral of f of z to z, but I'm going to use the path gamma. So what do? Well, we introduce all these points ti. Now, I could call these ti, but it's much simpler to actually partition the domain of gamma, 0, 1, by placing ti's here. In which case, this will not be ti, this will be gamma of ti. And this will not be t2, well, that won't be t1, that'll be gamma of t1. And this will be not t2, but that will be gamma of t2. And then I don't have to place sample points literally within the complex plane here. I can put sample points here, that's tau 2, and that's tau 1. I can put sample points in the domain of gamma, and then trust that they will be mapped onto the curve gamma. And so the sample points here are actually of the form gamma of tau 1, and then gamma of tau 2, etc. So basically what we're doing is we're populating the domain 0, 1 of the path gamma with the data necessary to produce all of the waypoints between A and B. And then we're actually getting the locations of the waypoints by, well, just translating them through gamma, right? Gamma of all of those values will give us the waypoints. Once we do this, gamma is basically solving all of our problems for us. We have a partition of 0, 1, and then we push everything forward by gamma, and that gives us the divisions, and it also gives us the sample points. And everything has the form gamma of something. So then, what would our Riemann sum be? It would be a limit of a summation. So I'm going to write the limit, but we'll talk about what the limit means in a minute. And then summation, I equals 1 to m. Now we need to evaluate the function at the sample points, but now notice the sample points within the complex plane are of the form gamma of ti. So that's f of gamma of ti. And then we need to calculate the difference between the two. So here we had ti minus 1, but that was because those were the two values in the domain of the function. Here, we need to calculate the difference of the values in the domain of the function, which is now gamma of ti minus gamma of ti minus 1. So this is going to be gamma ti minus gamma ti minus 1. So we have the difference there, and I'm going to rewrite this slightly because it's a little bit sloppy. So that's f of tau I times gamma of ti minus gamma of ti minus 1. So the reason now that I have gammas here is because those are the difference between the actual waypoints which are dividing in the domain of the function f. And so this is actually the value that should correspond to the ti's here, which are the waypoints in the domain of the function f. So we get f of tau I, and then gamma, when I rewrote it, I introduced an error. So that should be f of gamma of tau I times gamma ti minus gamma ti minus 1. So that will be the limit. Now, what do we know about the, what can we say about the nature of that limit? So here we have a limit as something happens. So what is that limit? We have a partition here. Now, we would like these points to get closer and closer to one another. Provided that gamma is a reasonable function, say gamma is a continuous function, when these points in the domain of gamma get close to each other, then these points in the range of gamma will likewise get close to each other. And so, assuming that gamma is continuous, we could actually define, we could force these things to get close to each other, which is what we actually want, by merely forcing these things to get close to each other. So in other words, if the norm of this partition of 0, 1 goes to 0, then this will give us exactly what we want. And so here, I'm just going to say partition norm goes to 0. And here, this is where P is a partition of the domain of gamma, not anything happening within the complex plane. So we began with the effort of, here, let's describe a partition on the real line, and then let's try to generalize it to a partition within the complex plane. But if you look closely at what's actually happened here, we've ended up with a partition of the real line again. In fact, we've ended up with a function gamma, which maps a portion of the real line here, and then the partition data is actually now again defined along the real line. So that, again, we have a partition on the reals and a function of the partition on the reals. And then everything else carries through, we just push it forward across gamma and then do the same thing that we tried to do before. So this gives us a definition of the path integral f of z dz, if it exists, right? Of course, this is a limit, and the limit has to exist in order for this thing to make any sense. So that's the path integral. Now, that alone is interesting enough that we can spend a lot of time studying it, but it has a curious little consequence here. The function f only appears in this formula composed with the function gamma. And f composed with gamma is a function from this closed interval into the complex numbers, right? F maps from the complexes to the complexes. So if you first apply gamma, get to the complexes, then apply f, stay to the complexes, then f composed gamma is a function from the interval to the complexes. Gamma is a different function from the interval to the complexes. But the function f appears only on the right-hand side in the context of it's getting composed with gamma. And that suggests an immediate generalization of this. We could simply put any function here, any function from the same domain that gamma has, into the complex numbers. And so let's introduce a notation for that in a minute, but let's actually introduce the definition first. So let me say more generally, so something that we could also consider is the limit as the partition norm goes to 0 of the summation I equals 1 to m of g of tau I times gamma of ti minus gamma of ti minus 1. So this is, well, this is different, right? So this is equal to this if g is the composition of f with gamma. But this must be a generalization of this, because here I could put any function at all here. It doesn't necessarily have to be a function which is composed with gamma. This deserves a different notation, and the notation we use for this is the integral of g d gamma. And now we either write this would be from 0 to 1. Here I have assumed, so if gamma maps, so now that, so if gamma maps 0 to 1 to the complex plane and g maps 0 to 1 to the complex plane, then we get this limit. But now we realize this restriction on gamma, that it has domain 0, 1, is kind of artificial. Any closed interval would do just as well. And so we can generalize this further, and we can let gamma and g both map any arbitrary closed interval, which now we might as well call A and B. And so we get from A to B here. So now, so here, where P partitions AB. So this is the limit of partitions of AB, and as their norm goes to 0, and then we get this function. So this is a complex valued function of the partition P, and this is the limit as it goes to 0. So this is called the Riemann-Stieltjes integral. So that's the Riemann-Stieltjes integral, d gamma. It's a strict generalization of the path integral. And let me point out how. So the path integral of gamma, f of z dz, is equal to the Riemann-Stieltjes integral from A to B of f circ gamma d gamma, right? So basically, you let the function g, in this definition, be f composed with gamma, and then this is the Riemann-Stieltjes, and then this is the path integral. Now, why do this generalization? I mean, it's obvious we can, but why should we? Well, the Riemann-Stieltjes integral generalizes the complex path integral, but it also, in a straightforward way, generalizes the Riemann integral itself. So I want to point out here that if this g plays the role of this f, and this gamma is simply the identity function on the integral, then this integral is also this integral. So we have the integral from A to B of g d gamma is equal to the integral from A to B of g of x dx. And that's the real sense. And I feel I've done something wrong. So this is the Riemann-Stieltjes, and this is true if gamma is the identity map on AB. And how do I know that? Because if you just compare what this says to what this says, when gamma is the identity map, you can drop the gammas from this notation, and you end up with this, right? So it's just as simple as looking at this and looking at this, and noticing that when gamma is the identity map, it drops out of the notation. And that means that this thing is equal to this thing, with the f has to be replaced with a g. So this thing is equal to this thing when gamma is the identity map. So that means that the Riemann-Stieltjes integral is a generalization of the ordinary Riemann integral, but in a different way is a generalization of the most important integral in complex calculus, which is the path integral. And that means that if we can develop one theory of integration for the Riemann-Stieltjes integral, then we can simply say, oh, well, it follows that integration theory works in the reals, and it also follows, by the way, that integration theory works for path integrals. And that's why, as we go forward, we're going to be focusing our attention on the Riemann-Stieltjes integral as the most important case. We will still have a little bit of work to do. We'll still have to figure out what conditions do we really want to impose upon gamma so that we can know that this limit is actually going to exist. And that's a little bit subtle and a little bit tricky, but there are nice conditions on gamma that make it work.